Princeton actually in a few months, so many of you got a chance to meet him. Are you around in the afternoon?
Until about 3?
Yeah, so you should use the opportunity, and he'll tell us about Traitor Tracing.
All right, so I'm going to try to keep this talk. Well, in crypto, we like to think of ourselves more as complexity theorists, but this is actually going to be much more of an algorithms type of talk. And please don't hesitate to stop me if you have any questions. Okay, so what is traitor tracing? I watched too many spy shows, so I'm going to use a spy example as motivation. This is this old show from the 60s and 70s called Get Smart, for those of you who don't recognize these characters. So up at the top we have Control, and down at the bottom here we have a bunch of spies working for Control. And Control wants to be able to send broadcasts to all of its spies. Now on the right here we have Chaos, who might be, that's the enemy of Control. They might be listening to all the communication. And we don't want Chaos to be able to learn what the messages that are being sent are. So the natural thing to do is Control is going to encrypt all of his broadcasts using some encryption scheme and give out secret keys to all of the spies so that the spies can decrypt the broadcasts. Meanwhile, Chaos over here, they don't get the secret key, so they should not be able to actually decrypt the broadcast. Okay, so where traitor tracing comes in is, suppose this spy on the right, spy dog Fang, decides that he actually wants to go work for Chaos, and he's going to leak the key that he was given. We really can't stop him from doing this. He can, write his key down on a piece of paper, throw it in a trash can, and Chaos comes by and picks it up. But what we can hope is that if we are somehow able to intercept the leaked key, that we can actually identify who it was that leaked the key. So the goal of traitor tracing is, if we actually are able to intercept the leaked key, we want to be able to identify the traitor who leaked it. And we want to do this for many reasons. One is we want to be able to revoke the key. Because if we can't revoke the key, otherwise this entire infrastructure is now useless because Chaos can read all of our messages. And we also want to be able to punish that user, and by punishing them, disincentivize them from being a traitor in the first place. So this is a spy example. You can also think of examples where this might be relevant in the context of content distribution. So your XM radio or something like that, these guys are all your subscribers. You want only your subscribers to be able to decrypt your radio broadcasts and any non-subscriber not to. But one of your subscribers breaks open his receiver, reads off the secret key inside of it and publishes it on the web. Or builds a pirate decoder box that he goes and sells for a profit. And in these cases, we want to be able to identify that user in order to fine them or prosecute them, and then ultimately revoke them as well. Okay, so there's some considerations that we want to think of when trying to design a traitor tracing scheme. So it should be clear at this point that everyone at least needs their own individual secret key. Because if we give everyone the same secret key, if you're trying to, given a leaked key, find out who it was, it looks the same regardless of who leaked the key. So you want some user-specific keys. So here I have a potential scheme. I'm just going to use the regular encryption scheme that we had, but append the user's identity to the key.
What happens if I just do this? I keep a list of all the users and the keys that they're using?
Mm-hmm. I mean, so that is a solution, but we would need everyone to have a separate secret key, right? And
but would you do that anyway, right?
Yeah, we would do that anyway. But we can't do something silly like just append their username to the key, because they could just rip off that username when they go to leak the key.
I just keep a list for myself with the names and their keys.
Right,
and
but
if I see the key, I look in the list and I know who key it was.
But I guess the question is, what are the keys? Are they keys for this?
Random strings.
They're just random strings. Well, now how do you actually encrypt so that everyone with these random strings can decrypt?
I use whatever crypto system you want to use. AES.
Mm-hmm. Yeah, so one solution that we'll talk about is basically everyone gets their own separate secret key for basically a separate instance of a crypto system. Ideally, we would want to do better than that.
You can only encrypt the key with the private keys. When you send a message, have a box, have a personal log box attached to it. But I guess it scales the number of users, which
right.
you probably don't want.
Yeah, so that's exactly what we're going to get to in a couple slides, is that we want to keep things from scaling too poorly with the number of users. But in any case, regardless of how you actually go about implementing it, it should be clear that every user needs their own secret key. We clearly can't use this sort of silly scheme where we just add their identity to the key, because they could just strip that identity off and leak the underlying key, and we have no way at that point of identifying the user. Now, the adversary can do a lot more here. We live in a world now in crypto where we can do crazy things, including obfuscating programs. So the adversary could take his secret key that he was given and construct a program that just uses the key to decrypt whatever ciphertext. And now he runs this through an obfuscator, which is basically just a compiler that hides all implementation details of the original program. So the output would be some program that actually decrypts, but presumably it would hide all the implementation details, including the secret key that went into the decryption procedure. And then also, what happens if the adversary is able to somehow take his key and break it in a way that allows the resulting broken key to decrypt half of the message, half the bits of the message, but maybe not the others. This is still a bad thing, even if the enemy only learns half of the message. So what we're going to do is assume that the traitor, rather than producing a key, is actually going to leak a pirate decoder, which is just some arbitrary function that takes as input a ciphertext and outputs just a single bit. So we want to even consider the case where the pirate decoder only leaks a single bit of the plain text. And then we also, in tracing, when we actually want to take the pirate decoder and find out who it was that was the traitor, we only want to give Oracle access to this tracing algorithm. If we're required to actually look at the code of the pirate decoder to figure out who the traitor was, we will probably run into issues with an adversary that tries to obfuscate the code. So we want to just interact with the pirate decoder by giving it ciphertext and seeing what it gives out. Okay, and then there's the question of what if there's more than one traitor? What if there are many double agents inside your spy organization? We really want to protect against this as well. So what we're going to do is allow the adversary to actually be able to corrupt as many users as he wants within the organization and get as many secret keys as he wants before trying to construct a pirate decoder. I just want to point out that the bounded collusion setting, where you say, I am going to assume there's no more than 5 traitors, is also a very interesting setting, but it's not what we will be considering today. Okay, so now I'm going to actually sort of formally define traitor tracing. So we have some syntax here. We have a setup procedure that outputs a master secret key and a public key. This public key is just public, anyone can see it, even the enemy. The secret key is kept by control. It's kept by the authority. We have an encryption procedure that just encrypts a message using a public key and outputs a ciphertext. And then we have a key generation procedure that, given the master secret key that's held by control and a user identity, which we'll just assume is an integer from 1 to some number n, it outputs that user's secret key. And now once the user has a secret key and a ciphertext, they can decrypt to get the message. And then finally, we have a tracing algorithm, which takes in a pirate decoder as just an oracle, as well as the public key, and it outputs some accused set of users. So it's going to try to figure out who given the pirate decoder, is going to try to figure out who the identities of the users who actually constructed the pirate decoder are. Okay, so we have some basic properties. One is correctness, that secret keys actually decrypt ciphertext. We have a basic security property that says that control, the enemy, can't decrypt anything if he doesn't have a secret key. And then we have a traceability property, and this is the more interesting property. So we're going to consider the following experiment, where we take a bunch of keys for various users, some subset T of all users, and give them to the traitor. The traitor is going to use those keys, do whatever he wants, and he's going to ultimately construct the pirate decoder box. We trace the pirate decoder box because we intercepted it, and get a set A of accused users.
Is it important that the public key is really public key, the encryption key? Because it's a central thing. You can just keep it also secret.
It's not important necessarily for the spy application, but it's just all the tools we'll use, we can easily get public key or secret key. They're sort of interchangeable, so public key is stronger because normally you can add authentication on top of that if you don't want to allow anyone to encrypt to the channel. So since we can get it, we might as well consider public keys. Okay, so the first requirement that definitely needs to hold is that if we accuse a set A of users, that set does not include any honest users who were not traitors. So otherwise the traitor could get people to be falsely accused, and that's obviously a bad thing. So we never want to accuse an honest user. And then we want to say that if the pirate decoder is useful, if it actually is able to decrypt messages, then the set of accused users is not empty. So if there is a useful pirate decoder, we're actually able to figure out at least one traitor from that pirate decoder that we can go accuse. And by the first property, we know that it actually will be one of the traitors and not an honest user. Okay.
So you put the picture.
Yeah.
So what's useful here?
I'm not formally defining useful, but useful learns a bit of information about the message, any bit.
So what does the traceability need? So the dog picture, say again.
So the tracing so we have the tracing algorithm, which just given Oracle access to the decoder.
Oracle access to the decoder.
Yeah. The decoder is produced by an adversary who's given some secret keys, and then we accuse some subset of those.
It's not just a few decoded in things like the dog picture. It's like Oracle access.
It's Oracle access, yeah.
The decoder has state, I mean, it remembers.
We're going to assume no state. So there's
try to figure out if it's being studied and
right. That's no. I mean that is a problem, and especially if you consider the pirate decoder being an actual physical box, like in the XM radio example, you construct a physical box that you go sell to someone. It might self-destruct after reading one message. Right, and that's something that some people have considered. It's beyond the scope of this work. We're going to assume a stateless decoder that we can just interact with as many times as we want. Okay, so as we were talking about before, there's actually a trivial traitor tracing system where for every user, there's a separate secret key for that user, and in the public key setting, a separate public key as well. And the ciphertext is just an encryption of the message under every single one of the keys. Tracing is actually very simple. We basically just we construct ciphertexts that have M encrypted under some of the secret keys and garbage under the others, and just see if the box decrypts. And it's not too difficult to create an efficient tracing algorithm from this. So the limitation are that the parameter sizes and running times grow linearly with the number of users. because for a ciphertext has a component for every single one of the receivers. And the tracing algorithm also runs in time n. So the goal is to minimize the parameter sizes. And another goal is that maybe we would want to handle an exponential size set of users, and we'll get into that more later. So yeah, so this has been the goal of Traitor Tracing for a while, is to minimize these parameter sizes. Okay, so some prior work. The prior work on Traitor Tracing can be broken down into basically 3 categories. So one are these combinatorial constructions where they just take any public key encryption scheme and play some clever tricks to get a Traitor Tracing system. All these combinatorial schemes are bounded in the bounded collusion setting. So they assume some prior bound, say 5, on the possible number of traitors. And they get a tracing system that works as long as the number of traitors is less than 5. Unfortunately, once you go to 6, they're completely broken, and you can actually get honest users to be falsely accused. But the state of the art is pretty good. Basically, all the parameter sizes only depend logarithmically on the number of users, but they grow polynomially in the size of the collusion. The second class is algebraic constructions. And these come in, there's both results that are bounded and unbounded. And the state of the art here is for unbounded collusions, we can actually get all the parameter sizes to grow with square root of the number of users. So we can actually do sublinear size parameters from these assumptions, but we don't know how to get the size down to, say, polylogarithmic in the number of users. The last category are ones based on obfuscation. So these are these very recent tools that have been developed. They rely on extremely strong assumptions, but we actually get optimal polylogarithmic dependence on the number of users.
So no dependence on k?
No dependence on k. So we, in the unbounded setting, you basically set k to be n.
No, in this.
K is n. Unbounded.
Yeah, and unbounded we
that's what you said.
yeah.
So IO is, we know this holds under some other assumption, or is it just an assumption?
So that's been, yeah, so IO stands for indistinguishability obfuscation, FE stands for functional encryption, and these are some recent tools that have been developed. We know IO from some assumptions, but those assumptions we now know to be false. So right now, the state is
linear maps?
yeah. So we can construct IO and FE from certain assumptions on multilinear maps. Those assumptions are false now.
How recent?
As of like a year ago. But the constructions themselves have resisted attack, even though the assumptions are based on are false. Just sort of a weird scenario. So right now, basically, they're assumptions. We have these candidate constructions. We believe, or a lot of us believe, that they're secure. But nonetheless, they are extremely strong because they basically imply in all of crypto. Okay. So the point where this work picks up is the question of who keeps track of the user info. So the tracing algorithm that we were given, after tracing, it returns a number from 1 to n of the index of the user who was the traitor. And now if we want to go and actually revoke that user, that's fine. We just know, okay, that secret key, don't send any more broadcasts to that. But how do we actually go and, say, prosecute that traitor? We're just given a number. In order to actually go and figure out who the person, the individual was who corresponded to that number, we need to keep track of which user corresponded to which number. So we might keep a database of user number and their address. Maybe in the case of content distribution, we keep their credit card number so that we can find them. Whatever other information you want, we keep this database. However, this approach has this really basically it requires this database to actually go and figure out the user. And if someone's keeping this database around, there's an inherent lack of privacy. Because now whoever's running the tracing algorithm actually is keeping your user data around. And so the question we ask is, are tracing and anonymity at odds in traitor tracing? So the starting point is, why not set the integer that is the user identity in the system? Why not set that to be some integer representation of the string containing their address and their credit card number, right? So we actually have their identity in the system be their identity in real life. Well, if the length of the identifying info is L, for an address and credit card number, I don't know what the amount of information is. Maybe it's 100 bits or something like that. We're going to need n, the number of users that the system can support, to be 2 to the L. And 2 to the 100 is a very big number. Not going to be actually, if things grow with n, this is not going to be efficient. And in current systems, n is a polynomial. It can be taken maybe to be in the billions or trillions. And this means that L is sort of inherently bounded to be pretty small, and really too small to embed arbitrary identifying information in it.
What was wrong with the identifier idea again? The previous one?
The problem is that someone has to maintain this database. Okay. And so having this database around is sort of an anonymity violation, because whoever it is that is going to actually trace and go prosecute must know the identities of all users, even the honest ones.
So in the new one, you will have this information, generate the secret key, and then dump it.
Yeah,
forget about this.
Exactly. We could presumably just not even keep this database around, and the only person who knows the identity of the users is the user themselves, unless they're a traitor, and then they get traced. Okay. So I guess the main takeaway is that in order to embed arbitrary info into the public key, we really needed an exponential size space of identities.
So who can decrypt this information? You?
Who can who can decrypt? Yeah. Well, so presumably no one, unless you actually leak your key.
And then somehow magically it's decodable.
Yeah, then it's decodable because you have this pirate decoder that you can run the tracing algorithm on to recover you.
Can I take the key that I sent you, create a pirate decoder of myself?
You'd have to, okay, yeah, you would have to remember the key though, right? Oh, so here is an example if we wanted to ensure anonymity. So the user wants to just, he has to produce his identifying information at some point, and he wants to get his secret key with that information embedded. And the say content distributor or the spy agency, they're keeping the master secret key around, but maybe we don't want them to learn the user's identity. So an example would be in the content distribution setting. An example would be that you're embarrassed that you're subscribing to a particular content, and you don't want the fact that you are subscribing to that content to be publicly known. You could maybe pay for it with anonymous cash like Bitcoin or something like that, so that your identity is completely hidden. But you still want to be able to, the content distributor still wants to be able to trace and learn your identifying information so that they can go after you should you leak your key. So we can actually accomplish this functionality of the two sides give their inputs. The one side gets their secret key, and the other side learns nothing about the user using a general multi-party computation protocol. Just as a little aside, we need to somehow verify that the user actually did give the right identifying info. So you'd need some sort of verification authority.
So what's the relationship between L and the security in the previous slide and the security parameter?
Yeah, so I've been more or less pushing the security parameter under the rug here.
But are you okay with the N being 2 to the security parameter, or that's too big?
Well, so it depends on the scheme. So with the current, with like the algebraic schemes where parameters grow with n to the 1/2, setting n to be some exponential number like 2 to the 128, your parameter sizes are going to be enormous, and you're never going to be able to actually instantiate the scheme.
Because if you believe in forgetting, then you could encrypt any amount of information, store it on the server, throw away the key, embed it into the identity. So instead of address credit card, you just need to store a key.
That's true. But that key still needs to contain some, the key needs to be, 128 bits.
It needs to be the size of the security parameter.
Yeah, exactly. So n needs to be exponential in the security parameter if your parameter, and if your ciphertexts grow with n, then you're in trouble. Right.
Actually, n is not so large because the number of addresses in the US is only 300 million or maybe 100 million.
Yeah. International spy agency, worldwide. Yeah, but maybe you want to have a picture being encoded in the key so you could put up wanted posters or,
It's a content distribution. Every device will have some kind of ID.
Yeah, I mean, I guess the way I think about this is making things much cleaner. You just, whatever information you want to be able to extract about the user when you go and trace them, you just throw it into the key. And you don't need to keep this database around or have the decoder box have an ID in it. Everything is right there in the key. All right, so the basic way that, at least in the unbounded collusion setting, basically all prior traitor tracing systems use this formula. They first build what's called a private linear broadcast encryption scheme. And I'll define what that is soon. And then they use this nice result of Bonnet, Sahai, and Waters, which shows how, given any private linear broadcast scheme, you can just generically add a tracing algorithm to it. And then you get a tracing algorithm with the exact same parameters. Okay, so what is private linear broadcast? So it's going to look very similar to tracing. All the users have their own individual secret keys. The main difference, or one of two main differences, is that now when you encrypt, you don't just encrypt the payload, you also specify an integer. And this integer says which subset of the users are going to be able to decrypt. So in this case, we said, okay, the integer we're specifying is 3, and that means the first 3 users can decrypt. But users 4 and 5 cannot. So it's a way of specifying certain very restricted subsets of users that can decrypt the message. From functionality, so basically we're encrypting to intervals, right? We can specify some interval of users. Those users can decrypt the broadcast and the rest cannot. And then
that's what linear refers to?
That's what the linear refers to, yeah. And then for security, well, we have sort of basic semantic security requirements that says those who are not supposed to receive the message cannot. But we actually also want to hide the interval itself as much as possible. So, clearly this guy, he learns some information about the interval just by virtue of being able to decrypt. He learns that the interval at least included him. And similarly, this guy, he can't decrypt, so he learns that the interval cannot or does not include him. But beyond that, we want there to be no extra information learned about the interval, beyond what is trivially implied by whether or not you can decrypt it. Okay.
You're going to need this secrecy.
That's important for tracing, this secrecy requirement, yeah. Okay, so here is the semantics. It looks very similar to the semantics for traitor tracing, except there's no tracing algorithm yet. And then we have one difference here, and that the encryption algorithm takes as input an extra input, which is a number from 0 to n. Properties, we have the correctness property that says if I encrypt to an interval and then I decrypt it with a user in that interval, that I can decrypt. We have semantic security, which says basically if I encrypt to no one, so 0 means if I give 0 as an input to the encryption algorithm, that means no one can decrypt. The security says that that's actually the case. Even if I give you all the secret keys for everyone, you can't decrypt. And then finally, we have recipient privacy, and this is the interval is hidden property. And this is easily formalized as follows. Basically, an encryption to an interval containing user U is indistinguishable from the interval with U removed, unless I actually have the key for that user. Okay. So given private linear broadcasts, we can actually trace. And here is roughly how it works. So I'm going to define this function. It's a function on the integer v that I set into the encryption algorithm. And basically the function is the probability that the pirate decoder produced by the traitor is able to decrypt a ciphertext encrypted with that index. And we can look at the function f, and these little red lines correspond to identities owned by the adversary. And I claim that basically between these little red lines, the function f doesn't change very much. But across these, once I hit one of these red lines, it's allowed to change arbitrarily. And the fact that they don't change between the red lines actually just follows from the security of the private linear broadcast. Right? Because if the pirate decoder, if say there was a jump here in between, this pirate decoder would break the recipient privacy property of the private linear broadcast. Because the decoder would be able to distinguish an encryption to an index U from U minus 1 without actually knowing the key for U.
So this, sorry.
The original functionality had no interval in it. Like you just wanted to broadcast to everybody.
The traitor tracing functionality did not have the interval, yes.
Right. But this forces you to. What if I want to use this key, but always I'm only going to broadcast to everybody?
Right. So that, I mean.
Box will also have this. So you wouldn't be able to do this.
Yeah. So I actually forgot to say what the actual traitor tracing system is. In the traitor tracing system, it just always encrypts to everyone.
But the box itself can also always just decrypt.
But you don't know,
But
I mean, if you could do that, you would learn whether it was encrypted to everyone or a part interval. You're not supposed to learn that.
Exactly. So suppose the pirate decoder was only going to try to decrypt things meant for everyone and just give up on things not meant for everyone. Well, if the pirate decoder, for example, does not have user n, he can't distinguish an encryption to everyone from an encryption to everyone but n.
What if he has that?
Well, if he has n, then he can distinguish, and we would be able to trace and tell that because we would see a big jump in this function here.
But this requires them to be put in nominal.
Exactly.
Right?
Yeah, exactly.
But you would always trace the same one. When
Would-
you give different sets, you always find, let's say, you might always just accuse the maximum, the one with the maximal, right?
But we will guarantee that you will trace to at least one bad guy, but we might miss all the rest. That's entirely possible. And
if my index is somewhere in the middle and I somehow get someone with a higher index to collaborate with me, I can be safe somehow.
Yeah, you could just trick them into constructing the pirate decoder completely by themselves, and there's nothing really we can do about that, right? If your key was not even used to construct the pirate decoder, we have no hope of learning your identity from the pirate decoder.
Then you have to go back to old-fashioned law enforcement, question the people.
Yeah. Or, if you combine traitor tracing with a revocation mechanism, you trace, you revoke that user, and now either the pirate decoder is completely broken, or if it still works, you can run the tracing algorithm again and keep tracing basically all of the users that caused the pirate decoder to work. You might still miss people, but if they want their keys to ultimately work, they're going to have to construct a new decoder at that point. Okay, so how do we actually do tracing? Well, first we start off by interacting with the decoder by just feeding him zero encryptions to the interval containing no one. And I'm going to define the probability, or I'm going to find P0 as a probability that he actually succeeds in decrypting. Then I do the same encrypting to the first guy, encrypting to the first two, all the way until I encrypt to everyone. And I get all of these probabilities. I'm really getting estimates of the probabilities. And these correspond to estimates for the function f. And now I just find where there's a jump, and I output those guys. Okay.
I guess you can also do binary search instead.
Yes, we'll get to that in a minute. Okay, so if we want to go to identity spaces that are exponential, we're in trouble, because the tracing time runs in time proportional to the number of identities, which will now be exponential time. So the tracing algorithm is not going to work. Fortunately, however, all of these private linear broadcast schemes that we have, yes, they're from extremely strong assumptions, but all the ones we have work just fine if the identity space is exponentially big. They're efficient and all that. So really the issue in constructing traitor tracing for large identity space is really the tracing algorithm.
So, but you can make it run in time polynomial, and it's slightly better. It's the time polynomial and the number of colluding parties. So if
well, we don't. But see, we don't know who the colluding parties are, right? And so they could be anywhere from 0 to n. So if n is an exponentially large number, we really have to.
You can do binary search and.
Yes. So we'll.
So if the number of participants was exponential, then you would be in real trouble, right? Because then it could jump a little bit every time.
Or even if it's 2, we'll get there in like 1 minute. Okay, so first thing we do is we're going to actually just abstract this problem that comes up in traitor tracing. This looks exactly like what we had before, but now there's no reference to traitor tracing. Basically, I'm given a function, Oracle access to a function. I'm guaranteed that there are several points, a polynomial number of points, in between which the function doesn't vary very much, but at these points it's allowed to jump. And my goal is to find the location of one of these jumps. You can see this clearly maps.
Question.
Yeah.
So since you're anyway assuming that we have only Oracle access to this program, right?
Yeah.
We don't understand it. So couldn't the program sort of detect that you're trying to trace and just shut down or leave garbage?
Yeah, we're assuming a stateless program.
Oh, you mentioned
yeah.
But yeah, so this is
like if it's software, this is fair, right?
What?
If the pirate decoder is software, it's fair to run it multiple times.
Oh, you shut it down.
Yeah. If it's a hardware thing, yeah, it could self-destruct or do something.
But is software really stateless? I mean, can't it sort of modify itself in a simple way?
Yeah, you can just you can copy the code. Yeah, yeah. Yeah, so in software this isn't an issue. In hardware it is an issue, and it's beyond the scope of this work, but it has been considered. Right. So we have this. We give this algorithmic problem that really a solution to this corresponds exactly to a tracing algorithm for a private linear broadcast. So the original Bonet-Sahai-Waters algorithm corresponds exactly to a linear search across the entire domain of the function to find where there is a jump. And since it visits every point, it runs linear in the number of inputs. For efficient tracing, we need something to be polylogarithmic in the number of inputs. And this means we can't visit every point in the domain. So the very natural thing to do is a binary search. And at first glance, this looks like it works. So here's what I do. I first query the function on the endpoints, as well as right in the middle. And I look to see where there's a gap. So between here, suppose I just have the one user for now. Between here, I don't have any users, and so I'm not going to have any jumps here. But between here, where I do have a user, I have this big jump. And so I just recurse on this side, and I query the midpoint of this interval. I see, oh, I have a jump on the left, so I go query the midpoint of that, and so forth.
Why are you concede in a second minus delta.
Right, because, so here's the problem. So epsilon is the total variation across the entire domain. This epsilon here in the smaller interval is the variation across this interval. And because I'm allowing some variation across this half.
But the variation would be up to the point. Okay, so but it won't happen again. It won't be 3 delta the next time, right?
It will actually. So let's say it's actually 0 here and epsilon here. Then in the midpoint, the function might be delta. So my gap here is going to be epsilon minus delta.
Assuming, okay, so assuming, say this was farther than 3/4, then the next point cannot be, you can only suffer damage of 2 delta.
Yeah, you're right.
Only because you're one jump.
Right. Assuming there's one jump, you can only suffer twice, once from the left and once from the right.
Yeah, you're exactly right. But I mean, in any case, this is a small factor. We think of delta as being something negligible, very tiny. Epsilon is something big and noticeable. So these small factors don't end up being a big problem. But yeah, you're right. It should just be 2 all the way down. Okay. Now what happens? Yeah.
But n is exponential. Can this thing just go up very slowly or delta at every step?
That actually violates the security property of the private linear broadcast, because we said for any 2 points, it has the distinguishing advantage is negligible.
So delta.
Delta, yeah. So if at this mid,
delta colluding parties, then.
But it's not. Oh, you know what? I actually I messed up on my security definition. That according to that definition, I think you're right that it could do this. What we really need is the intuitive definition that I can't distinguish encryptions unless I have a key that can actually decrypt one and not the other. So if say here, this was 0, this was 1/2, let's say. But if I don't have any key there, I'm basically distinguishing an encryption to no one from an encryption to the first half of the interval without a key that can decrypt one and not the other, and that's a violation of the security property. Yeah. So yeah, it really is that it's flat anywhere that you don't have a jump. Okay. So that one user, things look great. What happens if we have more than one user? So for example, here, when I start out, I do these 2 tests, and I actually see that there's jumps on both sides. What side do I recurse on for my, question?
Why does the number go down?
The adversary who's constructing the box, we're not going to make any assumptions. It seems like he's being counterproductive by making it go down, but maybe he makes it go down to try to confuse you or something like that. Yeah, not.
To hide the identities,
Yeah.
You can have a lot more users, fake users.
Right, so we can have it go up and down, and then maybe you can't, if you don't actually, you might not ever see that it goes up and down if you never actually query that in that small interval. I mean, that's actually what, in this example, exactly what's going to happen. Right, so we do our test and we see, oh, there's a jump here, there's a jump here. Neither one of them is the whole entire epsilon. They're both maybe about half epsilon. What side do we recurse on for binary search? Do we recurse on the one with the larger gap? That's sort of the first thing you might try. Unfortunately, the gap could decrease by as much as a factor of 2 every single recursion. So here on the entire interval, you have a gap between left and right of epsilon. Now, let's say this one's the one that's slightly bigger than epsilon over 2. The next time you recurse, it might be slightly bigger than epsilon over 4, and so forth. And you can actually come up with pathological examples where recursing on the larger gap really does lose you this factor of a half every time. And eventually, if you keep losing factor of a half, your epsilon will be, your variation will be lost within the noise delta here.
So recursion randomly proportionally to the gap wouldn't leave you ahead?
I don't think so. And part of the reason is the gap also doesn't really tell us about how many actual jumps there are within that interval.
So here you could be unlucky and recurse right, but you could be very lucky and recurse left.
Yeah. I haven't thought about it. It might work. I'm not sure.
The worst example is it just goes very, very slowly.
So then you just recurse uniformly and your success probability is something like 1 over the number of traitors, which you cannot beat with any of this. So
n is much bigger than 1 over delta.
But the critical parameter is the number of traitors, not n.
Yeah, but you don't. It might work.
Because even to detect differences that are smaller than some delta, you need time over delta, right?
Mm-hmm. Yeah. It might work. But that's not going to be the route we take. So the other thing you might think of, oh, what if I do both? What if I just recurse on both sides? If there's ever a large gap on both sides, I just do recurse on both. The question is this still polynomial time? And it turns out that it is. So this idea of recursing on both actually is not new to us. It's an algorithm we borrowed from Boyle, Chung, and Pass. They use it in an entirely different context. This is interesting that this algorithm pops up in many places. Yeah, so in this example, we see that there's a gap on both sides, so now we recurse on both intervals. And now say we're on the left here, we see there's only a gap on this side, so we're just going to recurse over here. And on this one, I'm going to assume these are too close. We don't detect a gap here, but we detect a gap here. And so we recurse on this interval and this interval, and then we just keep going. So why is this guaranteed to be polynomial time? It's actually not immediately obvious, but once you see this picture, I hope it becomes more clear. So we can think of the intervals that you can possibly recurse on as consisting of a tree. The root of the tree is just the entire space. Its children are the two intervals when you divide it in half, and their children similarly are just you keep dividing the interval in half to get the children. So the green guys represent intervals that we actually recursed on. And the blue guys represent intervals that don't have any traitors in them. And this weird color represents intervals that do have a traitor, but that we still did not recurse on. And the point is that if we ever recurse on an interval, it means there was a large variation across that interval. And by the security properties of our broadcast scheme, we know that that means there is a jump in that interval, right? Because you have very little variation as long as your interval doesn't have any bad guys in it. Yeah.
You said so for the two red dots in the middle, they're canceling each other out.
Yeah.
So why can't the adversary hide two red dots on the right side and two on the left side or something?
He could try that, but if all of his guys cancel out, over here he's going to be 0, and over here he's going to be 0 as well, because everything just exactly cancels out, right?